Oh, thanks, Elizabeth. I see Elizabeth just put the meeting agenda in the chat. If anyone is interested in pulling that up, I'll also show that in just a minute. We'll go ahead and get started. I mean, it looks like people are still trickling in, but just to kind of move things along, we have a full agenda. So I'll just start with a couple of introductions while people trickle in. So I'm Bill Sachs. I'm one of the co-chairs of the Software Engineering Working Group. And I'm in the CESM Software Engineering Group at NCAR, along with a new co-chair of the Software Engineering Working Group, Ligia Bernardet from NOAA. Ligia, do you want to introduce yourself briefly?
Sure.
So I'll stop sharing
sure.
so people can see you.
Okay. Sure, I'm Ligia Bernardet. I work at NOAA in Boulder at Global Systems Laboratory. So I've been working with NOAA models for quite a while, and I'm a scientist. I'm not a software engineer, but I do have an appreciation for things such as code management, public releases, documentation support. So that's the field I've been working with.
So we're really happy to have Ligia on board as the new co-chair, as there is kind of growing collaboration between NCAR CGD and NOAA in a variety of areas of software development, some of which you'll get to hear about this afternoon. So so we're happy to have you here. And I want to also just say thank you to the previous software engineering working group co-chairs who all recently stepped down, Mariana Bertenstein, Rob Jacob, and John Dennis. So thank you all. They all served the software engineering working group for many years before this change of co-chairs. So let me go ahead and start sharing again, just to share a couple of logistics for this afternoon. So we will have a couple hours of a series of talks this afternoon. And then in the later part of the afternoon, we'll have an extended discussion session on the wide range of work that's going on right now on CESM diagnostics packages and the development of new diagnostics packages. And so we hope that many people can stay for that and take part in that discussion. I think that should be an interesting and engaging discussion that we're interested in hearing feedback from everyone on. Just a few logistics. The meeting is being streamed to YouTube and being recorded. The chat will also be recorded. I've been told that includes private chat. So if you want to arrange a dinner date for after the meeting, use some other means. Please make sure your microphone is muted when you're not talking. For questions, we will hope to allow time for questions after each talk. And if you have a question, you can either raise your hand, which can be done using the reactions button in Zoom, or type your question or comment in the chat. Speakers, you do have a 15-minute slot. Just in the interest of allowing some time for questions, we hope you'll end around 12 minutes. We'll give you a 2-minute warning at the 10-minute mark. And I just want to also remind everyone of the NCAR and UCAR Code of Conduct. So please try to offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. So with that, I would like to introduce our first speaker, Anne Fuyu. I hope I'm pronouncing your last name close to correct, from the Nordic E-Infrastructure Collaboration, who's going to let us know about some work they're doing on techniques for packaging and distributing Earth system models. So Anne, if you want to share your screen and go ahead whenever you're ready.
Yes. Can you see the presentation?
Yes.
Yes. Okay, so I will talk about this Earth system model as a service. This is a work where I do with my colleague Jean-Jacques Winter, is working at the University of Oslo in Norway. And this is done in the context of two projects, Yoast Nordic and the NICES 2 project. So this is a brief outline of this presentation, first with the objective, requirement, and the approach. What we have done so far, and this is also where we would like to get feedback from you guys, and some conclusion and next steps. And we would be interested to have collaboration. There are many things we don't know, and that could be very helpful for us to make progress. So this is something that we would be interested at least. So the main objectives and the requirements, this is really to open up Earth system models to a wider range of users and to increase collaboration paths between scientists from different disciplines. So we have more and more requests from people not from the Earth system modeling community that would like to create their own scenario or one workflows, and they would like to do it in the context of climate change mitigation or climate change impact studies. So we would like to find a way to help them to do it properly. So we still would like to make it reproducible. So this is quite important, especially when you have non-specialists. And we would like to increase the fairness of Earth system models, but not only the data, it's mostly about tools and workflows. One of the requirements is to have a very low maintenance. So if we have a new version, ideally we just want a number to change a number, and everything should be done automatically, like from the deployment, test, validation, etc. So we would like to have like a single recipe for multiple usage and platforms, and everything should be automated and open source. So this is the approach, and we would start like with packaging. So what we do with any tool like CESM, we start to package, and we use package manager. So at the moment we are using Conda as a package manager, but ideally we could change it by anything. And then automatically we want to create containers. It can be Singularity, Docker, or whatever. So we are going on this on the right hand side. And this from once we have a container, we create what we call a tool, which is mostly like a container plus some additional metadata. So this is to increase the fairness. And we want to be able to use this tool within different workflow manager system to create workflows. And ideally, we would like to use any kind of workflow manager system that the end user could use, like Galaxy, Silk, SnakeMake, or whatever. And then we can go on the bottom side here. Everything should be able to be fair, so findable and reusable. So we would like to have some kind of registries where a user could search for tools, could search for containers, and could search for workflows and like experiments when they have run an experiment. In terms of infrastructure, we want to be agnostic from the underlying infrastructure, but we still want to have performance, so to be able to run on any cloud or existing Galaxy web server, if they exist, and on HPC, including exascale. So that's what we would like to do. What we have done so far, so we started, for instance, with CESM, and we started to package and to containerize. So ideally, we started to write like a small recipe for CESM. It's like a YAML file where we have all the requirements for using CESM, and we did the same for NorESM. NorESM is a Norwegian Earth system model. It's identical to CESM, except they have an ocean component where it is different, and the atmosphere is slightly different. Then from this, we automatically generate a Conda package, which you can download, and then the container, which you can download. And every time we have new version, it is updated automatically. So we did this, and then the next step was, but does it work? Does it scale? Does it is it efficient? So what we have started to do is we started on like virtual machines, and it works very well. And then we say, okay, let's try on a HPC. So we use Betsy. Betsy is the biggest national supercomputer in Norway. It's not maybe very big, but it's still the biggest for Norwegian. This is where they are running CMIP6 experiment. So here, this is the result for a relatively small configuration COMSET. This is a NorESM. This is NF2000 CLIMO, which is very similar to your F2000 CLIMO. It's in terms of performance a bit lower because it's additional aerosol, and it's quite low resolution. So here you have the model throughputs and simulated years per day, and this is the number of CPUs. And we try to see if the performance when we are running without a container or with a container are more or less identical. And we see there is not much performance loss as expected, because container run quite close to the hardware. So the next step was, okay, but can we do that if we take the same container and we run it on a completely new architecture or completely new machine, and we don't know the machine, and we deploy it in less than 1 hour? So we went on the Oracle Cloud Infrastructure, and they have like bare metal HPC, which you can combine to create a HPC cloud. So what we did, we took, so they have nodes, they have 36 processors, and we build a HPC cluster with 16 nodes, and we added a shared file system and big GFS, and then we deploy the container immediately just to see how it goes. As you can see, it's not that bad. As you increase the number of processors, you have some drop in performance here. This is related to big GFS. So we did absolutely nothing, no performance improvement. So this is what's really to test if it was efficient. So it's not too bad. It could be improved for sure. But we were quite happy with the results. So the next step was, okay, so we have the container. So now let's write a small wrapper, which is an XML wrapper, to create a tool. And then we can put the tool into a register, and then we can start to create workflows. So that's what we did. And then when you write an XML wrapper, you can add metadata. So we add some metadata for a small ontology for tools. So it can be searchable and findable, accessible, etc. And the main advantage of this XML wrapper is out of the box, without any additional work, you have a small graphical interface. It's not super fancy. I think you will show something much nicer later on, but it's still good enough for end user to build an experiment. And this is based from what I have chosen for inputs. I'm sure it can be improved, but that's the main idea. And from this, you also have a graphical interface. You can combine your like CESM here with other tools to make some workflows that you can share with end user. So when you get a workflow is just a text file, and we can convert it in a common workflow language, so it is interoperable. And you can register it in a register, for instance, and get a persistent identifier. If you have like result and visualization, or like a NetCDF output you want to share, what we want is to gather everything, at least like cross-reference, and put it in what we call a research object. And we would like to share it in a research object hub, where people could search, for instance, with text mining facility, some experiments that have been done somewhere in the world, and they could reuse the results. If you don't like the graphical interface, you can use other like command line or Jupyter Lab. It's really very flexible on how you can, the different interfaces you can access the same tool. Conclusion and next step. There are a lot of work still to do. There is no documentation mostly. We really would like to have a CESM as part of our training infrastructure as a service, which is a free service we are offering to everyone in the world, and they can book like a virtual classroom, and they can teach anything, like any tools. And we would like the CESM to be part of it, so have a small training material for this. Add some more different models. For instance, in the Nordic, we are using ECS, so it's probably something we need to add. I heard you are developing some new diagnostics, so it's probably maybe something useful to add as a post-process. We have started to containerize the NCAR VRM editor, and I think we could have like a use case where you can create your own grid, and then you create your experiment out of it. I think it could be maybe of added value, maybe something we could do as part of a training material. I don't know, but I would be happy to get any question, feedback, and as I said before, we would be very interested to collaborate in some ways. There are many things in the scripts we don't know, and we could do better, for instance. And that's it. You can stop sharing, sorry.
Thanks very much, Anne. That is really interesting and really good to hear about. We do have a few minutes for questions. I see one question in the chat that I'll start by reading from Peter Caldwell. Are you able to choose optimal PE layouts automatically as you move your container to different machines with different cores per node?
Yes. So, I mean, this is an area where I'm not so good because I don't know very well CESM. So I could see we could change this. We create this configuration machine where you can specify the number of processors per node. And they have this config PE layout, which I don't know very well how to make it best. So we try like a ad hoc algorithm, which seems to work, but I'm sure there are some improvements here.
Are there any other questions for Anne?
So I had this in the chat. When you first used the acronym FAIR, I wasn't sure what you meant by that, but you used it over a couple times, and I Googled it, and it said it was findable, accessibility, interoperability, and reusability. Can you educate me a little more on that?
Yeah, so and this is why I was talking about these registries, because one of the main problem we see for people not from the Earth system modeling community, or even not knowing, for instance, CESM, they don't even know how to search and what to search. So we really would like to improve this part where, and this is where I was talking at the end, we would like to have like text mining for searching experiment, because usually what they want to do is like to write a sentence. Is there anything with a double CO2 or something like that in the experiment? And we would like them to return all the experiment available in the world. Yeah. Yeah. Sorry, I should have mentioned it.
Okay. No, thank you for explaining. Yeah.
All right. There's a question.
Where did that?
Oh, go ahead.
Where did that come from? Where did the FAIR idea come from?
I think this is more from the data management world, which is probably where I'm coming from. Sorry.
Okay, cool. Thank you.
Rich Neal asks in the chat, for the regional grid generation tool, which software did you take that from? Is that an NCAR product or something else?
Yes. You mean this VRM editor? This is from NCAR. Yeah, we just containerize it because we thought we could make a small workflow out of it, but yeah, we did nothing. This is all yours.
I have a question, but it kind of ties together your talk and the upcoming talk, which is from Brian. So maybe I'll ask the question now, but we can hold off on answering it until after Brian's talk, which is I'm just interested to have a couple minutes of discussion on whether and how it would make sense to coordinate the kind of containerization and cloud activities of our two groups, since it seems like there's a lot of great work in that area and a lot of maybe similar overlap possibly. But again, yeah, maybe we can let Brian talk and just save a couple minutes at the end. After his
I mean,
talk.
I would be definitely very interested. I think we have lots to learn from you. There are many things we don't know, and we could incorporate. Thanks.
Okay. All right. Well, let's go on then to the next speaker is Brian Dobbins, if I'm remembering the schedule right. Yes, who will be telling us also about the kind of container and cloud activities that he's been working on for CESM. So Brian, take it away. Brian, you're muted, so.
That would help. All right, can everyone see my screen? Yes, thumbs up. All right.
Yes, we're good.
So yeah, this is great to go after Anne. I was really excited. So she was sending her slides to Elizabeth this morning, and I was like, I couldn't resist but looking at them because we have very similar design goals. So I'm already, I sent her an email already and said, this is really cool. I'd love to chat. So I'm hoping we can do that soon. So I'm a software engineer here in NCAR, and I colloquially call this effort CESM Everywhere, because the idea is we want to make CESM so easy to use and available everywhere. And we do that via containers and clouds. And I'm going to also talk a little about some future infrastructure. Hang on, there we go. All right, so there's three things I'm going to cover. So I'm going to talk about CESM platforms. You've kind of already gotten some of this from what Anne was saying, but maybe not in the same verbiage. Some infrastructure for the cloud, and then some database infrastructure, which is really cool. Databases don't excite people, but I'm hoping after this, you'll be pretty excited about what we can do. So what is a platform? So as everyone here who has tried to port CESM knows, it's a little complicated. You've got not just the code that we release, but also everything from an MPI library, compilers, netcdf, Git, Subversion. You got to customize some files. So what if in addition to just releasing code, we can also release platforms that people can just download and is all pre-configured and ready to go? And the answer is, well, this is what containers and clouds will let us do. So both cases in containers and clouds, we can pre-configure them with the full environment we want. And you can also standardize it. So one of the issues we have is that people on different systems, they have different versions of Python, different versions of the Intel compiler, different, we can standardize all that and make sure that there's a single platform that we know works the same for users. We can even standardize between the container and cloud platforms. So you can move from one to the other pretty transparently. So what's the difference between these? Well, containers are something that we use on existing hardware that you have access to. But clouds are something where you can rent hardware. You can actually run, of course, a container on rented cloud space as well, but that's the main difference is if you have stuff you want to use, you already own, you use a container. If you are just need more resources, you can use the cloud. So with both of these, yeah, we can kind of basically get people up and running in minutes. So we've done this with some grad students who were struggling to run CESM at the university, and we're like, hey, try this, and they're up and running in like 5 minutes. And there's still work to do, obviously, but it really makes a big difference. It even runs on Windows systems or Macs or Linux. You can run the container pretty much anywhere, which is a really big plus. One example of a platform is, so in addition to just CESM, we can combine this and do CESM plus a Jupyter Lab environment, add in the many Python packages that are in the standard Pangeo stack, and add in some tutorials. And now you have a standardized platform that works everywhere, works the same everywhere. This allows you to develop documentation to teach new users stuff. And so, this is an example from this CESM lab. And we will start releasing these tied to CESM releases in the near future. Okay, so I'm going to switch gears a little bit and talk about some cloud infrastructure. So everybody hears about the cloud, and if you listen to the vendors, they're like, oh, the cloud is, it's great. It's just, infinite scalability, and they talk about all the good sides of the cloud. They don't talk about how complex it is, and that's especially true with a model like CESM, which is already complex. So Peter Caldwell was asking about load balancing, and what happens when you have a cloud where you have 6 different node types and different network types and different processor types, and that's just one vendor. And then on top of that, you have multiple vendors. Each vendor has different region. Each region has different pricing. We don't want atmospheric scientists to kind of have to struggle through the cloud. We want them to just be able to say, I want to run this in the cloud and make a best choice on that. So an example of this is a recent use case. So a BW1850, this is a Wacom case. Amazon might be cheaper per node, but Azure scales better. So the same case, if you're running on Amazon, might be better on 8 nodes, but it might be better on 16 nodes on Azure. And better meaning cost optimal in this case. So it's complicated. So how are we addressing this? Well, we're going to create this cloud API that basically allows people to just say, hey, I want to run a cluster in the cloud, or I want to launch this job in the cloud. And we decouple those sorts of requests from all the backend logic that goes into determining what's best and then spinning up these cloud resources for people. We want to do this with their credentials so that we can't run everybody's runs for them. And so we don't store any credentials because that's a security problem, but we can update this functionality in a fully decoupled way so that, right now I have it sort of working with Amazon. It's still in development. We can add Azure as we get more access to that. We can add Google Cloud, and the user side still looks the same. So here's an example of this for creating a cluster. So on the left is just what you normally see as a user. On the right, I've added a lot of the verbosity just so you can kind of see the details of what's happening. So I run this command, CESM create cluster. This is an unreleased tool right now. We're still working on it. And what it does is it says, oh, okay, you're trying to create a cluster. Well, okay, you haven't given me any information on comp set or resolution, which are things that affect performance. And you're just saying optimize for cost. So it's only going to look at the cost of hardware for this. And it knows it's me. It's just doing a single user. You can do classroom use though with a list of users. It's going to query what clouds I have access to via my credentials, and then just spins up a cluster. All I get is an SSH command with an IP address, and that cluster will be fully ready to run CESM. And that cluster is fully compatible with the containerized version you can run on your laptop. In fact, this is where I'm not showing it here. I have it later because I know I'm going to run out of time. But if you wanted to run a laptop, you're running the container on your laptop, you want to offload a run to the cloud, it's just as easy as this as well. All right, so I know this is fast. I'm covering a lot of ground here. I'll switch one more moment to some database infrastructure. And so this is seemingly a different topic right now. We'll loop back to the cloud on the next slide. But we always have this big question of how is CESM being used? And I know that there are people that look through publications. We talk to people at conferences like this. We have some sense of that. But wouldn't it be better if we had actual data? And we can do this. We can set up a database that gets updates from runs. And we're not evil, so of course people can turn this off, and it's anonymized data anyway. But this would give us usage trends over time, and this is useful to pretty much everybody. So scientists can do meta-analysis of climate experiments. They can look for areas that are not being run, or resolutions that are not being run. CESM developers, we would love this because it informs us of trends. And one thing that, even model improvements, like we can collect metadata on source mods. We don't want to collect source mods because that's people doing work that they're going to be publishing, but we can say, hey, like which file was modified? And if we have a file that's modified often, maybe this informs us that we need to expose some of that functionality via name lists or some other stuff that doesn't require modifying source. And obviously NSF would love some high level view on CESM use, they would love that. So this is one use case for a metric, for a database. Another one, we talked a little bit about cloud runs. So in clouds, we can create clusters or we can create runs. We've seen some limitations with spinning up a cluster and trying to do large scale runs. So now we're looking at disconnected runs. So you just launch a run and it doesn't need to be connected to a cluster. This raises some questions though of what do you do with, you don't have a QStat and you don't have a persistent file system that you can just check on, see where your job is. So you need some status update of how your run is going. And this is ironically what things like PBS Pro and Slurm do is they use databases. So we're just kind of reinventing the wheel here. But because we're working for a specific application, we can return more than just how long it's been running or how long it's been sitting in the queue. We can return CESM specific information like what year it's on or what model date or expected finish time, simulated years per day, data volume. On top of that, we don't have to just track individual jobs. Like let's say that you had a 10,000 member parameter sweep and you could give it an ID that is a project. And you could track all 10,000 of those as one run and just kind of see what percentage done it is. And if you have a public database, I know most people here, we're always in front of our computers. We like to disconnect, but just in case you're off on the beach and you want to check your CESM runs, you could look at an app on your phone and see what the status is too. So there's a lot of potential here from this. So I know I'm running out of time. So I get really excited about, new functionality like this. So here are some other things you can do with a database. I'm going to go a little out of order because I think I saw Peter ask about load balancing and stuff. This is a really complicated task in CESM, as I think some of you know, and it's getting worse. And part of it is there's new components all the time. There's new hardware. There's variable resolution grids. So how do you know what an optimal layout is? And so one thing that we can do is we can sort of start setting up machine learning once we have enough data where you say, oh, well, you're on this kind of processor with this kind of network. You're running, this number of processors. We estimate this will be a good grid. And as we get more data, that gets better and better. It's I don't expect it to be perfect, but I think it'll beat sort of naive decompositions pretty quick. Finally, one other one I'll mention. Again. Let's say that you had let's say we were doing a parameter sweep between NCAR and 2 partner universities, and we set up 10,000 small runs that we wanted to do. Well, if you have a central database and a standard platform, you could have your systems opportunistically pull a run from the database that needs to be run it, and then notify the database it's done. And you can sort of distribute your computing here and coordinate with other universities or other partners. There's a lot of neat functionality that we can do here. I could go into more, but I think I'm pretty much out of time already. So I will pause and take questions. Thank you.
Great. Thank you very much, Brian. That's really excellent. Thanks for sharing that. Let's see. There's a couple of questions or comments in the chat. I'll start. There's I think it's just maybe a comment from Hendrik. The hidden costs of cloud data egress. I don't know.
Yeah, just intended as a comment. Our smaller one-off experiments in the cloud are fine. We're getting into real trouble when we try to link all the different data that we keep at different places. And so that may be actually also a problem with the last example that was given. If you spread the work between a whole bunch of people, then you do have to make sure that where the results are stored are such that you don't pay through the nose for getting all the data together in one place.
Sure. Yeah, we're seeing this now with a project that we're doing where, so academic institutions, I think, have a waiver of egress up to 15% of compute costs, but we found out only in the month in which you do the compute. So if you do 3 months of compute and then try to download all your data, nothing is waived. So this is definitely a problem that we've got to deal with. And there are, storing things in the cloud is great, but even if you do something distributed, we could use like Globus automated to transfer to a university right after the run. That minimizes it because you're doing it at the same time as compute. So there's a lot of options, but yeah, I agree. It's a messy, complex thing, and nobody wants big bills.
All right, let's see. There's a lot of...
You don't want to be a captive customer either.
Correct. Yes.
There's a lot of other questions coming in. Dave Bailey, I think Brian addressed your question about load balancing, but feel free to chime in if you have an additional question there. Peter Caldwell asked, could you imagine CESM doing its CMIP 7 runs on the cloud? Why or why not?
So we create the cloud capability primarily for external users. I don't see it being viable economically in terms of replacing something like Cheyenne or Duratio. It's simply too expensive on a large scale case. There are systems. So like, for example, again, this BW1850 case, we've got experience running this on AWS. We notice scaling problems, but Azure has a AMD Milan-based InfiniBand connected cluster, which is kind of similar to what Duratio is looking like and doesn't have the scalability. So performance is definitely fine. But again, the cost is just prohibitive for, compared to on-premise stuff. So I don't see it as being viable for something as large as CMIP 7 unless the cloud vendors wish to give us a whole lot of free credits. So, yeah.
Okay. Hannah Zanowski asks, could something like this be used at the classroom level? I'd be interested in having students try running the CESM like this, but I have no idea if this is feasible.
Sure. So absolutely. So that the catch is, yes, you can download. I can send you an email afterwards. You can download the container now, and you could run it on a simple laptop. The catch is you're going to be limited in terms of what you can run from the memory on your laptop. If you have a departmental server, that gives you a little bit more flexibility, but it just depends. So you can run, I can send you more information. You can't run like a fully coupled B1850 on a laptop because it requires like 80 or 90 gigs of RAM. But you can run a 4.5 degree atmosphere case or a lot of the simpler models. And that's something that we've seen a lot of interest in. And yeah, I'd love to chat with you more about that.
Great. Max Grover asks, where you talked about a run database, where would that run database be stored? Would you start with runs on the Glade file system or focus on new runs on the cloud?
Yeah, so that's a really interesting question. So we would store the database. This would be a cloud-based database just because we would avoid issues with NCAR's firewall, most likely by having it outside there. In terms of runs, this is something that we'd use moving forward. But this project did get its initial look by, I trawled through all of Scratch and found like 1 million timing files and loaded them into a database. Well, I should say, so we use databases for CESM where we have a timing database, we have an experiment database. These are kind of different databases. Like talking about databases, like talking about code. You have different kinds of applications and codes. We're talking about basically a key store NoSQL database for this. So it's much more scalable, much easier to use. And it's just all anonymized similar entries. But yeah, this would be on the cloud. We'd start with newer data because we want to collect additional information that's not currently in those timing files.
Cool. I'll ask one last, there's still a few more questions. I'll ask one last one from Anne about which metadata tags do you plan to add?
Right. So this is still a very open question. So, you know, there's questions there because if you have a public tool, you don't want to leave it fully open to anybody to add whatever they want because you might get, you know, strange things added. And so we're looking at, but we would like people to be able to tag like their work. And then you could maybe envision like a create clone command that can pull straight from a referenced work from a database or something like that. So there's a lot of things that I think we can add. And I think that the overall design of this is sort of orthogonal to the metadata tags. But the one I mentioned that I really am interested in is, again, we don't want to collect source mods, but we want data on which files are modified so that we can kind of maybe work on making them easier. So that's one bit of metadata I'd love to collect. Yeah.
Great. Well, thanks a lot. There's more coming in. There's a few more comments that I didn't repeat in the chat, as well as a couple of questions at the end. So if you get a chance to answer,
Great.
There's a question from Brian Medeiros and from Adriana Foster. If you get a chance to answer those in the chat, I'm sure you might appreciate it. And I will let, it sounds like you and Anne are already connecting, so that's great. So I'll let you guys maybe address, and I'd be happy to be part of a discussion. I'm sure a number of us would, on how we can coordinate these different cloud and container efforts between CESM and NOR-ESM, but we can take that offline. Thanks, Brian.
Thank you.
Next up, we have Alper Altuntis, who's going to be showing us some work he's been doing on putting together a graphical user interface for CESM, and in particular, the simpler models framework. So Alper, take it away.
Can you see my screen? Can you hear me, Bill?
Yeah, you're good. Yeah.
All right. So my name is Alper Altuntaş. I'm a software engineer at the oceanography section at NCAR. And more recently, I'm also working on this simpler models framework toolkits that we are developing for the broader CESM. And so I'll present a visual tool, a GUI, for users to create CESM cases. And the goal here we have is to streamline coupled and simple modeling within CESM, and also enable this idea of hierarchical modeling, where users can mix and match different model components with varying complexity and have a hierarchy of experiments models. And we have been developing several tools. I'll be talking about two of these tools: a new relational metadata and an associated infrastructure for that metadata to be processed, and also a graphical user interface. And so the emphasis here is on simpler modeling, but we also envision these tools to have a broader utilization beyond simpler modeling and within the broader CESM applications. So the tool chains that we have, we would like to provide a few key functionalities. First one I'll mention is that we want users to be able to query what's available within CESM, which is a lot of options, really, and we want to be able to list these options. We want to be able to visualize them for users to select from those options. And we also want to enable users to create their own custom configurations where they can mix and match different options, different model complexities. Like in this figure here, we have varying complexities, varying model selections for each component, and the user can select one of these and may want to know what other selections that they need to do to create a CESM experiment. So first, I'll briefly describe this new metadata to be incorporated in SEAM. This new metadata is going to be in a file, a YAML file that we call config comply. This sort of resembles our legacy config files, but the goal here is to express relatively complex interdependencies and incompatibilities between different options, like the ocean grid, what atmosphere component that we use, or what the mode that we have for a certain component. And these options might be specified in different config files, but within the config comply file, we can express some rules, some compliance rules to be checked and satisfied. And we also aim for this new metadata to be concise and highly expressive. And we want to be able to support arbitrary expressions in this new metadata. And the infrastructure that we are using is that this new file format is YAML. We are using YAML file format. And as for the syntax within this file, we can have arbitrary Python expressions in the forms of assertions that may include literals, logical or arithmetic operators, and SEAM case variables. And we developed a Python module to be added into SEAM that parses this new metadata, and then evaluator within the GUI tool that evaluates and determines whether any rules that we add in this file is satisfied or not. And here I have few examples from this file. As you can see, this is in YAML format, but also uses Python syntax. So I have 3 rules here that are specified by Python assertions. The first one being the simplest one, which says that CAM cannot be coupled with data. And here is the logical expression that enforces this assertion. Or we can have a little more involved rules, like land or ice must be present to hide mom6-bit posts, or when mom or pop is our ocean component, and when they are forced with data atmosphere, land must be stopped. So these sort of rules and relations can be expressed in this new metadata structure. So the next is the GUI that makes use of that metadata. And the purpose for this GUI is to guide the users through the process of creating CESM cases, and primarily choosing appropriate comp sets and grids. Here we use IPyWidgets module. This is a Python module that works on Jupyter Lab, and it's highly portable and I think widely used. And so we imagine this tool to be able to run on clusters, local machines, or even cloud and web. And I think Brian has some ideas on that front. Again, we don't expect users to be familiar with Python or Jupyter. It's fully graphical. And so now I'm going to a live demo, but before that, I should mention that the tool is still in an experimental stage, and it's a prototype with some of the key features not yet finalized. And with that, let me switch to a notebook. So all the user has to do now is to run this cell, Jupyter Notebook cell, which basically imports the GUI and then calls its display method. So when you run this, you'll get 2 consecutive dialogues. Step 1 is where the user selects some preliminary variables. And then once this preliminaries are confirmed, we move on to the second step, that is create case. So we can select from different drivers. And now here we have 2 modes, predefined and custom. So the predefined is where the user can query from already available configurations within CSM, already defined ones. And the custom one is where the user can create their own configurations. But let me first start with the predefined one. And I'll hit confirm. And I get to this new dialog, create case. So initially, so the ultimate goal here is to select the comp set and the grid, and then we can give it a case name and create the case. But initially we have 229 available comp sets. These are all of the comp sets that are defined in CESM. And we can narrow this down. For instance, we can let the GUI know that we only want to see the scientifically supported ones. And now I'm down to 27 available component sets. Or I can select these individual components. Maybe I know that my ocean components should be POP, and then I pick POP here. It narrows down. And perhaps for the atmosphere component, I can select data. It further narrows it down. And maybe I can add some keywords like JRA or eco, and it further narrows it down to 3 available comp sets. And I can pick one of these comp sets. And the second step now is to select from all available compatible grids. And once I pick a grid, I can give it a test or case name. And when I hit the create new case button, this will call the C create case command and run the or create the case for me. But going back, I now go into the custom mode. This is where I have a bit more flexibility. I can select from different initialization times. And this time I can also fine tune the components that I want to work with. For instance, if I pick CAM here, I can select from different CAM physics. And when I select different CAM physics, options get updated. And to get information about these options, I can hover over these buttons and I'll get the descriptions of these. And I'll just randomly pick some components here. And as you can see, as I make more decisions, make more selections here, some of the options become ineligible. So D-Wave, data wave here becomes ineligible. And if I click on this, I get an error message, invalid wave selection, MOM6 cannot be coupled with data wave component. And so if I want to make this data wave available again, I can change my ocean component to say POP, and then data wave becomes available. And when I pick data wave, now MOM6 becomes ineligible for the same exact reason. And
help her about 2 more minutes.
So once I make all these selections, I again get a comp set name. This is now a customized comp set that has not been defined in CESM, but I can again select a compatible grid and give it a case name and create my case. And going back to the slides, I have one final one. So just to list a few near-term goals, we need to improve and expand the metadata that we have that enforces those rules that guide the user. We want to add more features like the ability to define custom grids, not just the grids that are already defined. We want to provide more guidance. So those comp set names are still cryptic, and we want them to be more expressive and clear. And we are planning to establish automated testing. We have some ideas on that, and explore alternative logic solvers like the SMT satisfiability modular theory solvers. And hopefully we will be releasing a stable version for early users to experiment with this. But for those who would like to experiment with this raw version, it's publicly available in this GitHub repository. And with that, I will conclude.
Thanks a lot, Alper, for sharing this awesome work with us. And let's see, we have time for a couple questions. I do see a couple questions in the chat, so I'll start there. Steve Goldhaber asks, will YAML come with Seam, and what happens for users on environments where they cannot install new software? You can share your perspective, or I can share mine if you'd like.
Why don't you start?
Okay, well, I think this is a discussion we've had on and off in a number of contexts over the last few years, and I think my perspective on it is that we are in the near future going to need to require a couple of non-standard or third-party packages to Python. Probably the two that I think are most requested are YAML and a NetCDF package. So that's a bigger discussion, but I don't know if Alper, you have anything you want to add to that.
Yeah, I pretty much agree. And as for YAML, we also use it for our MOM6 nameless generator. And I know NOPSI uses it for some functionalities. So yeah, I think that's something we should be adding soon.
Cool. Adriana Foster asks if you can add alternative text to the buttons or alternate text. I'm not sure, Adriana, if you want to clarify.
Yeah, like it would be a way of making it more descriptive. Like, so instead of having like a bunch of bullets, this is what this is, you could just have an alt text like, oh, I don't know. Yeah, it was just an idea.
Yeah, I guess there are still certainly rooms for improvements in terms of making things less cryptic and more early user friendly. And yeah, you should be exploring those mechanisms like alt text.
Let's see, one last question, and I'll ask for now. Would this GUI be portable for non-NCAR machines? Maybe ties in with the earlier question.
Yes, and in fact, I was running this GUI on my local laptop, and it runs on Cheyenne or other machines as well. And I think Brian plans to package this and containerize it, and that way it could be virtually run on any machine.
Cool. Thanks again, Alper. There's a couple more comments and another question from Anne in the chat about licensing, but in the interest of time, I'll let you take a look at the chat when you get a chance, and we will move on to the last speaker before a short break, who is John Dennis from CESL Group at NCAR, who's going to give us an overview of GPU enablement activities in STP and the ASAP group. So John, whenever you're ready, go ahead, please.
Oh, I'm going to unmute myself. All right. Hopefully everybody can see and hear me now. So thank you for this opportunity. I'm going to give an overview of STP and ASAP. They're two groups, and I'll mention who those people are here. But first, something of an outline. So I'm just going to acknowledge the people that have worked on this project, or the 4 projects. 2 of them are going to be relevant for CSM, and 2 of them are not within CSM, but they're just kind of informational about what we're working on. So the acknowledgements are the Application Scalability Performance Group. This is a group that I lead at within CESL, and also special technical projects for STP. So the team members here, there's quite this work that I'm going to be describing here represents a lot of people's work. I probably have missed some people, and I apologize for that. But I tried to get as many as I could remember. So some of the funding for this work is from NSF Earthworks base funding, and also through NOAA, through the EOL laboratory. So again, 4 projects that we've been working on. The first one is the parameterization for unified microphysics across scales. So this is PUMIS, and this is sub-grid scale, sub-micro scale processes that drive the formation and evolution of clouds and precipitation particles. And so this is a picture here of all these processes that are going on. This is a microphysics package that is, I believe, the default now in CAM. And so some of the details of this GPU port. Why did we go after it? Well, it consumes about 5% of the total CAM execution time, and it only had 0.6% of the total CAM volume. So, so CAM and CSM in general is a very large code base, and so this looked like as easy of an entry in as far as impact versus code volume. So there was code changes that included the addition of directives, open ACC directives into the code for both the Pumas code and also for the CAM code. You can see the kind of the source lines of code changes there. So a modest amount of directives in both Pumas and in CAM. It did touch a lot of different subroutines because of the deep call stack that is used in this code. And so we have provided these modified versions of the code back into multiple repositories, the Pumas repositories, the CAM, and the SEAM repository. And those have been accepted. So the status of this code right now, as far as execution time for the MG3 or the Pumas code, is you can see in this table. It's the configuration that we're running is an F2000 Climo 2-degree, and we are placing this 2-degree model on a single node and or GPU. So this is a rather large, dense, or it's a rather large problem for a single node. And so you have when we set P columns equal to 16, which is the default used in CSM, you have the execution times there, and you also have the 384 P columns. So what you see here is that the GPU enablement really doesn't quite break even yet, even on this rather large problem on a single node, and but it does. So it runs. I guess it runs faster than the PGI compiler on Casper with this very large P columns size. So that was with MG3 and Pumas. Some other work, and this is. I was very involved in the previous section. I'm going to be less involved in this one. So we're going to oscillate here. So this is for work that's the model for predictions across scales for the pass atmosphere. So this is in a version of MPass-A, and I believe it's being integrated into CAM as a dynamical core. So the approach here is so there's there's the call stack. They moved most of the code onto the GPU. There were certain sections of the code that were not really compatible with the GPU, that being the land surface, the NOAA land surface model diagnostics, and shortwave and long wave radiation. And so the CPU part of this is actually handling both the offload and the other components that do not play well with the GPU. So this was kind of timing results from the ballot about 2 years ago. They have since improved the message passing characteristics. I did not include that. So what this is showing is, so for an MPass-A at 10 kilometers, 56 vertical levels, we're seeing about a 3x decrease in I guess increase in days per hour for the Summit versus Cheyenne. Summit does, or the GPU version does not scale quite as well, and this is due to issues with how they handle the message passing boundary exchanges. This is something that's been done within the last year or so. Anyway, so MPAS. Another project, and this is one that I've been very involved with, is the spline analysis at mesoscale utilizing radar and aircraft instrumentation. So what this is they would take an aircraft and they would fly it through like a thunderstorm or a hurricane or something like this, and it would take Doppler radar and it would bounce off the particles that were in the storm. And then this code essentially addresses the question, what did we just fly through? And then it reconstructs the field into an initial condition or that could be used for a numerical weather prediction. So you see the image here, you see the little black plane. As it's flying around the eye of the eye of the hurricane here. This was work. So this was initially a C++ code that was written in achieved parallelism through OpenMP. So we kind of radically improved the performance of this code, and we also put it on a GPU because it was well designed for this. So here's some execution times for, again, the comparison of the Intel Broadwell. So that's Cheyenne versus the NVIDIA V100. You have two cases here, Supercell and Hurricane. They have different characteristics as far as the physical domain that you're solving for versus the observation. And so you see about a factor of over 2 to 3 speed up for the Cheyenne node versus the NVIDIA V100. So if you look at the broader kind of end-to-end performance of when we started working on this code to the end result, we ended up getting a factor of 100x speed up. This was from the original version of the code on CPU to NVIDIA V100. So it dropped from about 600 minutes down to a little over 5 minutes to run this. So quite a significant speed up. And a lot of this was, there was multi-layers of speed up. There was some numerical speed up that Alison Baker helped with that achieved about a factor of 8 speed up. You got about a factor of 4 speed up from the hardware, and then then the remainder speed up came from just run-of-the-mill code optimizations. So finally, the fourth project is MURAM. This is a solar model for simulations of the Earth's atmosphere.
About 2 more minutes.
Okay. And so this has been jointly developed by HOA, the Max Planck Institute. This was, again, using OpenACC, had to kind of, this was not just an addition of OpenACC directives, but rather had to rewrite some of the algorithm, and because of its challenging kind of algorithm perspectives. So here's a scaling curve. Again, the green is the NVIDIA, and the blue is the Intel, and so that you have the throughput there. So you see about a factor 2 to 3 impact on speed up. So and then finally, one more thing here before the end. We're trying to create a community of practice. There's a GPU Tiger team meeting, and what we want to do is we want to regularly communicate ongoing GPU activities, training on skills, sharings of success, failures, tips, and techniques. This meeting, it's going to include a lightning round talks, and I have some suggestions for some lightning round items. That's going to be July 1st, and if you're interested, there's a register or send your slides with Mick Cody. So any questions?
All right. Thanks a lot, John, for sharing that great overview of all those activities. Yeah, I'll wait a minute to see if anyone has any questions. Feel free to put questions in the chat or ask John.
So I'll ask a question. It sounds like you're focused on OpenACC directives. Are there other approaches that you're considering?
Well, yes, we have been focused on ACC directives. I think the productivity, C++ productivity frameworks are interesting. We don't have any direct experience with that yet. This might be COCOS or this might be OneAPI. We will have that by the end of summer. But based upon the code bases that we have around here that are created over a number of years, and the directive seems to be the most viable at the moment.
Okay, thanks.
All right. Anne asks in the chat, how many person months did you need for this work? Curious to know the effort this took.
Well, if you have, it really depends upon the project. I mean, some of the projects were like 4 FTE months. Some of them were, closer to 2 to 3 years. So probably the quickest one also had the most spectacular results, which was the Samurai that had 4 to 5 FTE months effort. CSM was rather long. The MPAS was quite expensive as well. So.
All right. Well, thanks again, and thanks to all the speakers in this first section. We are going to take about a 10-minute break, so we're turning at 15 minutes past the hour. So get up and stretch, do whatever you need to do. There may or may not be coffee and cookies in your kitchen if you'd like to go get those. And we'll see you in about 10 minutes.
Can you hear me?
Yes.
Should I, great, should I try to share my screen just to make sure?
Yeah, go ahead. You can go ahead. I'll stop.
Is it working?
Yes.
Yes. Just put it in presentation mode if you can. Yep. That's great.
Let me dry run for a sec too. I mean, we can confuse everybody, Mariana, and just do each other's presentation.
Hendrik, it's all yours.
I was going to say we can confuse everybody by switching our presentations.
Oh yeah, that'd be great.
All right, let's see if I can do this. Share. It says sharing now. Let's see if I can actually present something. Too many clicks in these things. Okay, do you guys see my screen? Oh, my title slide?
Yep.
Yeah, it's great. Yep.
And obviously the sound check worked too. That's good. And that means I'll stop sharing.
All right, I'll go back to sharing.
And I'll be right back.
Okay. Got it.
Okay. It is 2:15, so we're going to resume our session. This is Ligia. I will chair this part of the program. For the speakers, again, you have 15 minutes, but we need to fit the speaker change in there as well as the questions. So I will give you a warning at 10 minutes and ask you that you please stop talking at 12 to 13 minutes so we have time for the questions. And please remember to put your presentation in present mode. Mariana, yours is already there. So with that, let's go ahead and get started. We're going to have Mariana Bertenstein, and she's going to talk to us, give us an update on the new ESMF NUOPSI coupling infrastructure, CMAPs, and the data models, CDEPs. So,
thank you. Can you hear me, Lisa? Everything's good.
Okay.
Thank you for giving me the opportunity to talk about this. I'm really excited about the progress that we've made over the last year. So I'm going to give a super brief overview on what ESMF NUOPSI is. Apologies to those of you that are already super familiar with this, but there might be people on the meeting that are not, so I'll explain it. And then I'll delve into progress we've made with the new CMAPs coupling infrastructure between components, as well as the new data models that we created and are being extensively used both by CSM and the NOAA project, which will be talked about a little bit later, and that is CDEPs. And I'll be defining all of these acronyms. So what is ESMF NUOPSI? ESMF is the Earth System Modeling Framework, and it is a community developed and governed infrastructure designed to flexibly couple components of an Earth system model together and it targets high performance capabilities and is very scalable. One of the additions to the ESMF package that was done several years ago is called the NUOPSI layer, which is the National Unified Operational Prediction Capability. That is a big mouthful, but it comes along with ESMF. And what it does is that it's standardized and made it easier to create a coupled model by introducing 4 new generic components that could be customized. And those would be the NUOPSI driver, NUOPSI model, which would be used for a component, and mediator, which I'll be talking about extensively in the next few slides, and the connector, which enables different components of the coupled model system to couple together and exchange data. So in terms of coupling between components, we've introduced this new mediator, which I'll define in a second, called CMEPS, that stands for the Community Mediator for Earth Prediction Systems. It is shared between CSM and the Unified Forecast System as NOAA as part of the NCAR NOAA MOA, and it's gone into operations as NOAA. We will be officially releasing it for CSM 2.3, but we already have beta tags with CMEPS capability, and I'll give you a quick outline in a little bit of where that stands. So what do we mean by the coupling infrastructure? As users of CSM know, it is a hub and spoke architecture. That means that the components of the system don't directly exchange data with each other, but rather they exchange data with a central coupler that can run on its own cores. And that central coupler is responsible for regridding the data from a source component to a target component, and then merging data that's been regridded from a collection of source components to the right correct target component. As you can see here, another part of the system is that for each of these components, we have the ability to swap out data components for the prognostic component as part of configuring an experiment. Now, the current coupler was based on MCT coupler 7, which has been in place for many years and has served CSM quite well. But what we're doing now is exchanging that coupler 7 hub to what we call a NUOPSI CMEPS hub. And that implies that now the components need to have another translation cap at the top layer called the NUOPSI cap that translates between the component data structures and the ESMF NUOPSI data structures. And as a result, this mediator NUOPSI CMEPS can be exchanged between component modeling systems, but is essential to a lot of the new capabilities that we are now exploring in CSM. And just to let you know, what I've circled here, SI6, MOM6, and WaveWatch 3, these are components that are used simultaneously by the NOAA Unified Forecast System, NOAA Unified Forecast System and CSM. And with SI6 and MOM6, they actually share a NUOPSI cap, and we're going to be exploring over the summer how to create a unified NUOPSI cap for WaveWatch. But in addition, with this same coupling infrastructure, we can also run the UFS atmosphere, but in a completely different modeling framework, which is the UFS. So I've picked, there are a lot of benefits to CMEPS, but I've picked 4 that I think really illustrate how this will enhance CSM science moving forward. First one is it's going to be much easier to introduce new grids to the system. For one thing, ESMF provides online mapping between source and destination components. And as a result, you're no longer going to need most of the mapping files that you have. You'll still need custom mapping files, which require smoothing like run up to ocean. So in coupler 7, you had 25 mapping files you needed to create for a B1850 case between the different components. Sorry, with CMEPS, you have 4. That's a huge reduction in maintenance and need to initialize the system. Another one that has been introduced very recently is the removal of the need to create domain files, which for the ocean and the land and particularly CLN describe what the land fraction was. The way in CSM you get the land fraction is you take an ocean mass, you map it to the land grid, and that gives you the land fraction on the atmosphere land grid, because in all our cases, we run the atmosphere and land on the same grid. In Coupler 7, each new component grid required you to use an offline tool to generate these domain files, and then you had to update SEAM with them. And that was a headache because it implied a lot of offline steps and updates to SEAM to do that. With CMEPS, you no longer need domain files. As an example, in CLM, you now take an ocean mesh, and at initialization time, you dynamically map it to the land grid, and that gives you the land fraction. So these are real big simplifications in how you can introduce new custom maps into your system. Another big simplification is what we're doing for land ice development in terms of coupling both Antarctica and Greenland in one simulation. Gokhan referred to this briefly yesterday. With Coupler 7, what we were going to do, which we never started, was to create a unified global grid for the system. That implied that for every combination of Greenland and Antarctica, or potentially other new ice sheets, you would have had to do a new unified grid, which would have resulted in a combinatoric explosion. With CMEPS, ESMF provides this really nifty capability where you could create nested states inside your state, where each nested state corresponds to a different ice sheet. And the flexibility of NUOPSI is that each of these nested states couples one to one with a corresponding ice sheet in the mediator. As a result, this is very extensible. You can keep adding new ice sheets, and there really is not any change you need to put into the mediator. It automatically recognizes that and does the regridding and merging. And our hope is to have this in a beta tag this summer. Another nice feature is what would happen with ocean land ice coupling. This requires actually coupling to multiple levels of the ocean beneath the land ice, and that each multiple level has a different bathymetry. So when this was explored in MCT, the way it was done is that each level had required a different mapping file because you had a different mask. Again, you can imagine if you were going to try to extend this along with the combinatoric nightmare of different ice sheets, it just becomes unfeasible to think of how this could have been supported. So what we can do with CMEPS is they have the ability to do dynamic masking. And so we can pass all the fields as one and regrid them all in the mediator with the dynamic mask of each bathymetry level and not have to introduce any mapping files at all. This is hot off the press. We have the ability now that I think will have a very large performance impact on CSM, which is the ability to have different components that share cores run with different threading levels. And this was simply not available with the Coupler 7 infrastructure. So in Coupler 7, if component A was threaded 4 ways and component B was not threaded and they shared nodes, you could only use a quarter of the cores in a node. With CMEPS, this restriction has been removed. And just to show you the latest timings for a B1850, you can see that the model cost is significantly reduced, and at the same time, the throughput is better. So I think this will have, like I said, a very significant impact on the cost of running simulations as well as throughput as we start optimizing and leveraging this capability. And finally, what we have is a dynamic ASCII file that is runtime that determines the sequencing of the system with a very simple syntax. And the run the run sequence can be changed without recompiling. The status of CMEPS is that all new science is being done with CMEPS. We're targeting it for CSM 2.3 and above for the default coupling infrastructure, and it's fundamental to several collaborations. Along with CMEPS, we have a new set of data models that are also based on ESMF NUOPSI. They are effectively a total refactor and extension of the Coupler 7 data models. So the key point of these new data models is that they support runtime regridding with more than just bilinear, which is what Coupler 7 provided. With CDEPs, you can do runtime regridding between a forcing data set and a target model grid. That includes not just bilinear, as with Coupler 7, that was done at runtime, but also conservative, nearest neighbor. And you can also do online 3D regridding. We've also, as part of CDEPs, put in new modularity to add specific science data models functionality and a total rewrite of how the XML input looks for these streams. So another capability of CMAPs is the ability to use this share code within a prognostic component. So if you look at what our current data models look like, you have in purple the forcing data, where these are streams that share a common grid and temporal frequency. And what the data model does is that it uses these different streams and maps them both in time and spatially to get data fields on the model grid that are then filled in with potentially missing data or other science requirements to create the fields that are then sent to CMAPs. But a really big new addition, which was also available in Coupler 7, but is much more extensible now because of the capabilities of the CDEP share code, is for a prognostic component such as CAM or CTSM to directly use this share code capability to do interpolation. And particularly for CAM, we're going to be looking at using this for aerosol forcing. The HEMCO group is very interested in migrating to this for looking at aerosol forcing for the chemistry, as well as other applications for nudging. So where CDEPs is coming in is that all validation is currently being done with CDEPs and CMAPs together. It has been available as of CSM 2.3 Beta 02. And it's, again, fundamental to several collaborative efforts that we have, including the NSF Earthwork efforts. It's being integrated into the Unified Forecast System, and it will be targeted for CSM 2.3 as the default data model. And again, both CMAPs and CDEPs are being jointly developed between NOAA and NCAR as part of the MOA. And I really want to call out that none of this would have really existed without the tremendous input of the ESMF core group, which is located at NCAR and CGD. They have been tremendously responsive about addressing any hiccups and problems we ran into, and especially this new efficiency that I showed was very much put in place as a collaboration between CSEG and the ESMF core group working together. And with that, hopefully I've made my time. So thank you, and I'm happy to take questions.
Okay, I think we have time just for a couple of quick questions. One, I think Jim already answered, but if you have any comments for an F case, which ocean mesh would you use for making the land mask without a domain file?
Do you want me to answer that, or did Jim answer that?
I think Jim answered. Do you want to add anything?
I haven't looked at what Jim said. So the point is, if you have a GX1B7 ocean, the ocean always has a mask of 1 or 0. So it depends on what your complementary, if you're running a B1850 at F19G17, your ocean mask is G17. And that's put into the land name list. That's a new feature in the land that you have to pick. It really depends on what complementary ocean model you want to be running.
Okay, that helps. Thanks.
Okay, so we're going to do one more and then we're going to move on from Robert Halberg. When you change the order of the component calls at runtime, is there the ability to change which fluxes are calculated explicitly or implicitly for each component?
So that's a good question. So when UFS uses it, they calculate the atmosphere ocean fluxes in the atmosphere. When CSM uses it, we calculate the atmosphere ocean fluxes in the mediator. I don't believe that either formulation, for sure, the formulation in CSM is not implicit. but we are looking at bringing in implicit formulations into the mediator using the exchange grid. And that is an ongoing effort that started right now. So where you actually calculate the atmosphere ocean fluxes is really independent of the sequence that you would put them in. So we have a very definite place in the sequence where it makes sense to calculate those and then use that to be sent to the atmosphere. And again, the exact same medium is being used by the UFS, but no atmosphere ocean fluxes are being calculated. So that particular phase of the mediator is never invoked in the run sequence.
Okay, we're going to have to move on. Thank you, Mariana. Hendrik, you can take the screen over if Mariana would stop there. And Hendrik Thoman will talk to us, will give us an update on the unified forecast system.
Sounds good. Can you hear me?
Yes, we can.
You can see my screen, I assume?
Yes.
All right. So it's a pleasure to be here at the CESM meeting. I think that in a few more years, we might have to deliberately hold joint CESM and UFS meetings, but we'll get there, cross the bridge when we get there. So I'm talking here for the UFS community, so it's just my name on there, but the reality is that that's a large group of people, and a lot of those people are in both communities, the CESM and the UFS. So bottom line up front, why is NOAA going to the UFS? Simplification of the production suite, basically applications from nowcast to seasonal, but not 9 months out. By law, we can go about 2 years out. Accelerate R2O by doing research and operations with the same tools, and broaden the base, having a bigger group of people looking at the models that we're using for research and operations. So this used to be just an idea, but it's really become a reality the last 18 months because we have some code releases and we actually have some of the UFS now in operations. And then the UFS is really joined at the hip through the infrastructure with the CESM, due to particularly the NCAR, Weather Service OER, MOA on infrastructure that Mariana already mentioned, and the fact that Mariana already mentioned that we have quite a few shared components. About the UFS, you probably have seen this before. I'm going to go through my slides pretty quick because, of course, I have way too many, but the idea is that we have a community code that is used both for research and operations, that our governance is evidence-based, decision-making based. The scope is on applications, so we have actionable outcomes and not just papers to write. The idea is to have a unified system and not a unitary system where we balance focus on a smaller number of ways of doing business while still at the same time assuring that we have the diversity we need for research. And then it's really a paradigm shift in the sense that we not, especially for our weather models, had been inward looking more than outward looking for quite a while, although that's not been the case for all our other component models. So in a nutshell, I could talk about this for at least half an hour, easy enough, but most of you will have seen the figures on the right. The key elements to do there is that the assistant administrators of the leaders of the line offices in NOAA are 100% behind this. That's kind of clear that from the fact that we have set up a unified modeling committee about 5 years ago to make sure that we looked at how we could simplify the work we're doing and how we could go to community modeling. The MOA was already mentioned, the fact that all our codes are now available on GitHub and things like that. The fact that we are doing research and operations with the same code. And another big thing is the fact that NOAA has sort of formalized their commitment to the UFS by setting up a large UFS R2O project that spends multiple years and multiple applications with a focus on getting UFS into operations. And then more recently, a few months ago, we have set up a NOAA modeling board, which coordinates within NOAA all the modeling efforts. And along that same time, the same week, the EPIC contract, the Earth Prediction Innovation Center contract, was awarded, which is going to put a lot more resources in specifically the infrastructure building for the UFS. And of course, that can be directly leveraged by the CESM. And so is this a theory, is this practice? Well, we really are a reality and not just an idea. The two key things that prove that is the fact that we have now a graduate student test where you can literally install some of our applications in a matter of a day, literally in a day, in 6 hours, where that used to take months and some people needed to buy their own supercomputer just to have the same computer that we had. The other thing that really makes this a reality is supported code releases. We have 2 code releases so far of the medium range weather application. I'll get back to that in a sec. One of the short range application, and then we have infrastructure components and tools, as well as some related to us JEDI data assimilation releases very recently. I won't go through all the details here, but these are some of the details of the previous slide. In blue are the different releases that we've had. So 2 medium range weather and 1 short range weather application. And in red are the actual implementations and operations that are associated with that. What really makes life different for us now is when you go further down to this area where we talk about the short range weather. We are not expecting our FE3 limited area model to be operational until about 2024, but we already have a fully supported application where we can work with the research community to work on operations. Before, what we before did was sharing this after we went into operation. So this really changes the timeline of collaboration massively. And what we're looking at now is having a other medium range weather application possibly late this year, or possibly looking at a hurricane application late this year. But this is the same thing. This would be if it is the global model, it will be the coupled seasonal subseasonal prototype. And again, we would be basically sharing that with the community, order of 3 to 4 to 5 years perhaps before we go into operations. And I don't want, even with the short time I have, I don't want to miss the opportunity to say that there's a lot more. It's the MET, CCCPP, CMAPS, JEDI, all these things and tools are all part of the bigger picture of the fact that this becomes a reality. So the R2O acceleration, we had some proof pre-UFS that pointed us in the direction of doing this community modeling effort. The wave model and the hurricane model are the examples of that, where we show that if we do full community modeling, we can accelerate the R2O process by a factor 3 to 5. For the wave model, it was going from 5 to 6 to 7 years for a new model to go into operations, to be able to do the equivalent of a new model in under 18 months. For HWRF, we basically see that instead of having 1 or 2 innovations per year, we now do have 3 to 5 innovations per year that can go into operations. And of course, what we've seen with the tool is that we leverage the investment of a much larger group of collaborators than our internal team. For the UFS itself, it's a little early to assess what the impact is on the R2O acceleration. But we had a very interesting situation in March that for the first time in many, many years, our global model actually was beating the European Center model on the standard anomaly correlation measures for a full week. And I hadn't seen that happen in at least 5 years. So that's boding well, but it's no hard proof yet. So UFS and CESM in a few things. Mariana already talked about some things of that, and we talked already about the MOA on the infrastructure. Just a few examples here, and this is this session is a good example of why we collaborate very well, because normally I would be talking for about an hour about this, but now Mariana, Ufuk, and Dom are all talking about elements of things that I don't have to talk about, and that shows you essentially how well we already collaborate on a lot of things. And of course, it's really neat to see that we actually not only share infrastructure, but that we have coupled component codes that are all shared between the two systems too. So there are differences between CESM and UFS, which helps us create both diversity and identifying cases where we can leverage. So applications are different. We are looking mostly at nowcast to seasonal, whereas a CESM is traditionally looking at decadal and centennial. There are different component models, although there's a lot of overlap right now. There are also different metrics that we use in a different forecast or outlook ranges. And we also see, and this is probably the one place in the MOA that we haven't quite completely got together, is on the workflow. So SEAM is used in CESM and in some of the UFS applications, but we've also recognized that we need multiple workflow solutions for multiple applications in the UFS. I'll get back to that in the next few slides. So the basic principles for the UFS, again, it's unified, not unitary. And so we have to have a balance between focus on on having tools that work, but also diversity when needed. And that basically means that we're looking at modular tools rather than a one-size-fits-all. And of course, with the UFS, and with any kind of place where you want to go forward rapidly, you start from functional requirements and not from solutions. And so we were looking at software engineering perspective and at the system engineering perspective. And to really summarize very quickly a very long discussion, we came to the conclusion that one size does not fit all. We have places where it's really important to limit the latency between model runs and data assimilation, in which case we really need to run the models out of the data assimilation environment. But we also have places where the resource requirements are so different between data assimilation and initialization and the actual model run that it makes much more sense to run them separately. And this comes up with a matrix of elements and a modular library approach that we are sort of contemplating right now for workflow. And what I'm showing then the next slide is highly tentative, is not a final solution, but just giving you an idea of what we're thinking. So if you take along the top, the functional aspects of a run in operations with going from input to initialization to model to product generation, and then the functional separation from having the actual program to wrapping that in scripts, setting configurations up, and running schedulers creates a matrix of all kinds of things that needs to be done. If you have some, yep, I'm almost done. If you have one step further, then you can look at what you do with these things. But the red part here is really all about things that we could share, and then on the blue part on the bottom, we would build separate solutions for separate applications. Last but not least, we are talking within NOAA between UFS and GFDL not being unified with the climate models and the shorter part. So we're working on that. It's an ongoing discussion, and there's particularly issues with differences in infrastructure. And with UFS and CESM, we're really looking at our coupled prototype for seasonal and sub-seasonal applications as being a potential bridge between the communities. Therefore, I will talk a little bit about this prototype. This is where we started, atmosphere, ocean, waves, and ice with the NEMS and CMAPS driver. The GitHub link there is to the unoriginal start. The first 4 prototypes we were running were really based on different types of initialization that we could do. And then since then, we have 2 more prototypes that have been completed and functioning on, focusing on getting into newer ice model, using the fractional grids that Mariana was talking about, and unifying the vertical structure of our atmospheric models. We also now went to a full NEMS mediator, and we started to merge all our global code. So there's a different GitHub link for that part. Without going too much into detail, this actually does work pretty well for us already, particularly looking at how the ice came out of our coupled model without any tuning or anything like that. Black lines is what observations are. The gray whiskers are how badly our CFS v2 drifts away from that in 45 days. And then the red and blue lines are different initializations that show that the coupled model without any tuning with the newer components to it actually does a heck of a lot better job already than the CFS v2. Same thing for another one of the prototypes, not time for discussing that. So leaving it at this for what I want to talk about right now, and hopefully having a few minutes for questions still.
All right, thank you, Hendrik. I don't see any question in the chat yet. We probably have time for one quick question. So while I don't see any question, I'll ask one. So the first public release of the UFS medium range radar application was done using the CESM workflow, right? Or at least part of it, the CESM case control system. You mentioned the possibility of a new public release at the end of this year of a coupled system. How are thoughts evolving about using the CESM case control for that release versus alternatives?
That is still open for discussion, so I can give you an idea where we're going, but those are not to be interpreted as final answers. So we are definitely looking, if you looked at that matrix plot over the top of it, central configuration management is something that is a key part of workflow. And so that is something that we're definitely looking at using CESM for still. In terms of being able to run something effectively in operations and research, we are working with NCAR and with other parts of NOAA actively on trying to figure out how that is working best in practice. And so we see a very clear benefit of CESM as a whole in terms of managing experiments, but we also see that there are things in there that are unnecessary overheads and not necessarily always the most effective way of doing business and operations. And considering how our collaborations have been so far, I am pretty sure that at the end of this discussion, everybody will benefit from it, and we're definitely looking at, from the NOAA perspective, like with other things that we've been able to pick up from NCAR, we see a lot of benefit in that. And the nice thing of this whole MOA has been that it's been the other way around too, because the whole CMAP setup is really based for a big part out of the original NEMS development we did before that. So there's been a lot of give and take, and it is really, really fun to go these days to meetings and have basically people like Mariana and I be tag teaming, and we were making the joke before the start of the session. We can basically do each other's presentations by now, and that I think bodes pretty well for collaboration. And this is all about functionality now that the discussion is no longer about solutions, and so that gives me the trust that we will get something out of it both.
Okay, due to the time, we're going to have to move on. So thank you, Hendrik. There is another question on the chat, so perhaps you can answer there directly. So Ufuk, you can please start sharing your presentation. And Ufuk will talk to us about the development and use of CDAPs in the UFS.
Hi, can you see my screen?
Yes, looks good.
Okay. Is there any echo or? No, that's fine. Okay, I will talk a little bit more about CDAPs and its integration with the Unified Forecast System, the UFS. So at the beginning of my talk, I just want to mention about all the people that contributes this work. So it's a really a effort of a large group at this point. So the main motivation behind of integrating CDAPs to UFS model is to support the hierarchical model development. This basically enables developing and building a modeling system systematically just by getting leveraging the data components and using them in a different purpose. At this point, the data components can replace the active model components. This will give you a capability to control the feedbacks between the different components of the modeling system. And it helps the user to understand the sensitivity of the underlying modeling components to different forcing. So you can easily switch, turn on and turn off the feedbacks between the different components. It also reduces the overhead, computational overhead in the development phase, because if you are using fully coupled system in a high resolution, you have to wait in a queue, and then you have to, the development goes a little bit hard with that kinds of way. So if you want to focus particular part of the modeling system and then trying to develop something over there, you can get benefit of the data components. Also, the time spent in debugging and testing is reduced at this point. So you can just isolate as individual components and then try to focus that one to solve existing problem or issues in there. And also the using of data components allow you to fill the grid points outside of the unmapped, outside of the active coupling region. This is basically important for the regional application, because in regional applications, for example, HAFS, the hurricane project, the domains of the individual model components doesn't overlap entirely, and then you have to blend the data coming from the files with the data coming from the coupler. So the data components could really help to solve those kinds of situations. And also, you can use the data components for the data assimilation. So the data atmosphere, for example, forcing can be used for the marine DA application that couples the ocean and ice components together. CDEPS is basically a fully ESMF NoAPSI complaint data model, so it can be used in another system because it's a standard interface. It's modular and flexible because it's written in a standard interface, and then this is proven by the integrating it into the UFS modeling system. The main building block of CDEPS is the data stream. So the data stream is something like a optimal interpolation sea surface temperature, the ERA 5 data set or something like that. So you can use different data set to define the data stream, and then these data streams could have same spatial and temporal coordinates, and also the data models could have multiple input streams. So you can combine multiple input streams together to feed an active component in here. It has lots of benefits in CDEPS. So you can have automated regrading capability provided by ESMF NoAPSI. So it can support different interpolation types, bilinear, conservative. Also, it supports temporal interpolation. So you have different options for temporal interpolation. This is important because the model coupling time step could be higher than the time step between the data time slices. So because of that, you might need to have temporal interpolation in there. And just my animation before, it provides also inline data model functionality. You can easily call the data components inside of the active or prognostic model component. So the NOAA UFS system currently adopting the CDEPS along with the CMAPS mediator. So sharing CDEPS between the organizations such as NCAR and NOAA has to bring new features and new data streams and community contributions to CDEPS, and that will lead to the benefit of NCAR CSM model also, because at the end of the day, all those pieces will be shared, and then all those different modeling systems could use the same code base. If you look at the UFS modeling system, we have two different applications for CDEPS. For example, one is for HAUS, another one for S2S application. The currently HAUS has two different modes, one for data atmosphere, another for data ocean. So you can feed the FE3 with data ocean through the CDEPS. In S2S side, there is only one implementation. They are only using the CDEPS data atmosphere, but CDEPS also provides other data components, for example, wave, ice, runoff, glacier, everything. So it's a matter of time to implement other data components, use other data components through the configuration of those applications. If you look at the supported data streams under UFS, you will see different variety of the components in different variety of streams in here. So the first one that's used under HAUS is the ERA 5. It's a well-known reanalysis data sets produced by ECMWF. Another option is NOAA optimal interpolation sea surface temperature. We are also looking for the possibilities of global high resolution sea surface temperature and R2FS data sets to use as a data ocean component. In S2S, they have two different data streams, one for CFSR, another one for GEFS. So it's getting more and more. So you can, for example, you can use ERA 5 in the S2S application, or you can use optimal interpolation sea surface temperature in the S2S application, because all of them is using the same code base at this point. What's the main difference between the, okay, before saying the difference between them, the UFS model had already a custom written, custom developed data atmosphere before. So the CDEPS is basically replacing that one. So the main difference between these two different data components, CDEPS will give you more data components. For example, the data ocean, data ice, data wave, rather than NAMS has only data atmosphere. And CDEPS also use the ESMF mesh rather than using the ESMF grid. ESMF mesh will give you more capability to represent different application, regional, global, different grids. So it's much more flexible at this point. And the NAMS data atmosphere only supports the linear interpolation in the time axis, but CDEP supports different kinds of interpolation in time. So nearest linear or if you want to do some kinds of radiation interpolation in time, you might want to represent the diurnal cycle of it. So there are some kinds of options for it. And also CDEPs also provides some capability for extrapolation. So if you don't have data, but if you want to run the model, you have some kinds of options. You can cycle the data, or you can use the last data or first data for it. So there are lots of different capabilities over there, including the inline data components capability. The validation of CDEPs under UFS weather model is initially done in the HAFS application and also STS application. In the STS application, they just want to compare the NAMS data atmosphere with the CDEPs data atmosphere to see the difference between them. And under HAFS, we are just looking for the creating a better forecast for the hurricanes. So there is also another validation done by Evan and Samuel from NOAA. But the initial results indicates that the CDEPs is able to reproduce the results of original NAMS provided data atmosphere. So I will show some example about that in my next slide. So if you look at these plots, the first one belongs to custom data atmosphere. The second one in here belongs to CDEPs data atmosphere. And then the last row is the difference between them. So as you can see, they are creating a very similar results at this point. So the difference between them is very small. So
10-minute warning.
Okay, thanks. So if you look at the CIs, it's same. So they are producing very similar results. So this is an initial validation, but it will be done. The more detailed validation will be done later. And if you look at the HAFS application, using the data atmosphere will improve the forecast. Of course, because you are using some kinds of observational data in here, and that observational data will improve the forecast and track of the hurricane. And as a summary, so the CDEPs has been integrated to UFS model and used by the HAFS and STS applications. It's a really collaborative work between NOAA, CRS, and NCAR. The current version of UFS has also NAMS data atmosphere because we want to keep them side by side for a short period until the validation is over. And CDEPs enables data model developers to perform hierarchical testing by selectively disabling feedbacks between the coupled modeling system. And sharing CDEPs across the modeling across the organization brings new data source that's not available in the CSM before, and enables to test CDEPs in a more broad way to find the problems in the CDEP site, and then this leads to a more robust software. And CDEPs could be also be a part of the data simulation workflow. If you want to look at it's included in the CSM, the last beta snapshot. It's also included in the UFS, so you can use UFS or CSM to reach the CDEPs to look at its structure. So that's all in my side. If you have any question, just let me know.
Okay, thank you, Ufuk. We have time for a question or two. I don't see any in the chat yet, so I'll ask the question. You mentioned this possibility of CDEPs being used as part of the DA workflow. How would that work? What's that?
Yeah, currently under STS application, the Marine DA group is trying to use CDEPs in their DA workflow. So I don't know too much detail about that work, but there are some possibilities. So recently we had a couple of chats with DA group, and then we did some presentation to them to possible usage directions in terms of the DA application. So at this point, it's evolving with small steps, but until we have a fully integrated CDEPs, I think it will be much more apparent for the other users.
Okay, well, there's no more questions here in the chat, so we're going to move on. And thank you, Ufuk. Other questions, if they come up, please just type them in the chat. And our next speaker will be Dom Heinzeller, and he will talk to us about the Common Community Physics Package, CCPP, sharing physics across NOAA and NCAR models using a common software framework.
All right, thank you, Lisa. Can you see my presentation?
Yes, can you put it on present mode?
I just need to get rid of the closed captions. Okay, here we go.
Yep,
that will work. All right, so good afternoon, everyone. My name is Dom Heinzeller. I'm a scientist at NOAA GSL, and on behalf of the CCPP Framework Developer Team, I would like to give you an update on the Common Community Physics Package CCPP, on our efforts for sharing physics across NOAA and NCAR models using a common software framework. So rewind the clock a bit to 2017 when we started working on the CCPP. Initially, it was planned or developed as a UFS infrastructure for atmospheric physics, and the original verbiage is to facilitate the improvement of physical parameterizations and their transition from research to operations by enabling the community to participate in the development and testing. Quite a mouthful. CCPP consists of 3 different repositories or packages. There is the CCPP Framework Infrastructure component, the CCPP Physics, a pool of compliant physical parameterizations, and then there is CCPP Doc, contains the technical documentation. While it was initially planned for physics only, it turns out that aerosols have been added recently, so we're adding a chemistry component. And the idea behind this, and I'm going to come back to this later, is that these aerosols can be either called as a NUOPSI component, or they can be called inline as a CCPP physics option. CCPP was built to accelerate the transition of innovations from research to operations, back to research, or just from research to research, so enabling this. So to this end, it has been developed as a model agnostic component that lowers the bar to add new schemes or transfer them between models. It's also an essential part of the hierarchical system development framework, HSD, that Ufuk mentioned beforehand. It's been implemented in the single column model with the idea behind that you can test physics in simple models where the process understanding is large, before you go to the fully coupled 3-dimensional model that are expensive to run and often very complicated to understand. Let me see, I cannot, okay. All right, just to remind everyone, CCPP relies on documented interfaces, which we refer to as metadata. So at compile time, the CCPP framework looks at metadata tables for each of the CCPP physics schemes that describe the variables that are required to run the physics. It also looks on the host model side for metadata tables that describe the variables that are provided. And by one of their attributes, the CCPP standard name, it connects these variables and then auto-generates caps. And these caps can sit under the atmosphere driver in a traditional way, which we refer to as slow physics, but they can also be inside the DICOR to run physics that we call fast physics because they run on the shorter acoustic time step. Yes, CCPP relies on suite definition files that are passed to the build system, and then CCPP generates the code. So I wanted to note that while that construct of having suites is an important one because that's more for the operational side in terms of a vetted combination of schemes that's known to run well and work well together. We also support this idea of an easy interchange of schemes within these suite definition files so that the research side can do its testing and have this flexibility that it needs. In any ways, this is a full suite definition file. It's called FE3 GFS version 16 beta. It's actually the same one as the FE3 GFS version 16 operational suite, but this was the original one that I put in here. And it's probably much longer than many of you have expected it to be. You would have expected things like radiation and then PBL, convection, and microphysics. And the reason for this is that in the CCPP world, there is no physics driver anymore. So these gigantic files that can be up to 40,000 lines long, like for example in WRF, all this glue code that connects the different schemes this glue code has to become a scheme itself. And we call these schemes interstitial schemes because they sit in between the actual primary schemes that do the work that you know, like PBL or convection. We'll come back to this. All right. A couple of features to point out. CCPP supports groups. That means you can call a group individually, or you can call all groups as they are listed in the suite definition file in that order. We have a capability to subcycle schemes that can be used for iterations or for calling them at a higher frequency or with a shorter time step. That has recently been introduced for Thomson microphysics and tested now. And the order of the schemes is up to the user. Of course, care must be taken if you swap the order of schemes, because some of this glue code in these interstitial schemes, for example, RTMG shortwave pre, RTMG shortwave post, and so some of this depends on the order. While it's safe in this case, radiation shortwave long wave, we have tested it. There may be other combinations where it's not that easy. So one needs to know what, users need to know what they are doing when they swap schemes. All right. The metadata that I mentioned beforehand is not only used to auto-generate the caps, it's also used to generate scientific documentation. So here's an example from the latest public release of the CCPP version 5.0 that was released as part of the short-range weather app version 1.0. And you see that the argument table that is used to create the interface in these auto-generated caps is also used as part of this documentation here to help the developers. So going forward in time, in 2019, the NOAA-NCAR Memorandum of Agreement was signed, as you all know. And as part of this, we identified contributions that NCAR was going to make to the CCPP framework within the CEMA program. The most important ones are listed here: an augmented metadata standard, which has already been adopted in the UFS, the ability to automatically allocate variables that are used by the physics only and that the host model doesn't have to know about, the ability to compare metadata to actual Fortran code, an improved build system and code generator, and advancements for chemistry, constituents, for example, and further. So that path to converging towards the common CCPP framework is sort of, we're coming from two sides and trying to get together by the end of 2022. So we started in 2017 with that first generation code generator, CCPP prebuild.py. We integrated that CCPP version in the DTC single column model, in NRL Neptune, small Neptune, and in the NOAA UFS. And then we went and looked at the requirements for a joint CCPP framework between NCAR and NOAA. And so we made several improvements to that first generation code generator in these, that are highlighted in these red boxes here, in order to get to a common code base or a point where we can transition. So these are the updated metadata format that I mentioned beforehand, automatic unit conversions, support for block data structures, additional CCPP phases that were required for the CSM, for example, and then a new metadata standard and rules on how to create standard names. At the same time, the NCAR side, most notably Steve, was working on the second generation code generator, captain.py. The early prototype was tested in the NCAR MICAM model, and then progress was a little slower, but within this year, 2021, we hope to have this version implemented in the NCAR MPAS model, then in the UFS, in SCM, in CESM, and then also in Neptune. And at this point, we will truly be using one version of the CCPP framework across all models. All right, I mentioned on the last slide that we are working on a metadata standard and rules. So there is a GitHub repository, CCPP standard names under the ESComp organization. And this repository is meant to contain community accepted CCPP standard names, publishing tools, search tools, and soon also rules for how to create new standard names. So there's an active discussion on the contents of this repository and also on the way to utilize it. Currently, there are 2 open PRs with updated standard names. That's about 2/3 of the standard names that are used in the UFS. And there are rules and a PR for rules for creating new names. So if you're interested in this process, I encourage you to go to that website and take a look at the issues, the pull requests, and the discussion therein. Another activity that is not coding in itself is that code management for shared physics and chemistry. So we are trying to develop a process for joint code management and testing of physics and chemistry. This involves multiple organizations and multiple modeling systems, and is thus far from being easy. That's an effort that is led by Ligia Bernardet and Mike Eck from NCAR-DTC. We have somewhat regular meetings, and we also have a Slack channel. If you're not included yet and you would like to be, let me know, or Ligia or Mike, and we can sign you up.
10 minutes down.
Yep. So CCPP provides opportunities for future development, especially after transitioning to the new code generator capgen.py. And I just want to mention a few highlights here. One is automatic array transformations from IKJ to IK or KI, and so on, or the ability to calculate derived variables, for example, potential temperature from temperature and geopotential. Or tools that help developers, such as a visualization tool, which is like a flow graph of a certain variable through a CCPP suite, where it's completely overwritten, where it's just read in, where it's modified, and so on. Additionally, we have the ideas to work on automated saving of physics scheme states for restart, extended diagnostic output capabilities from schemes, and then something that's being worked on actively, improved handling of constituent arrays and properties. Two more, these ones are not funded, or at least not entirely funded. The ability to create CCPP or NUAPSI caps for physics, so that a developer can decide at build time whether he wants to run a component as an inline component in CCPP or as an external component through NUAPSI. And primary candidate, of course, is the land surface model. And then the ability to generate optimized caps to dispatch physics on CPUs or GPUs, which is certainly required for next generation HPCs. And I'm happy to report that we have got some seed funding from NOAA GSL to try this with a few schemes with one of our models here in-house. So to wrap up, the enhanced interoperability and the ability to tap into the research community and connect them with operations makes CCPP an important tool for NOAA, NCAR, and other organizations. And the hope is that this will help to improve the current and next generation modeling systems used across these organizations. I would like to end with a short advertisement. There is a special issue in air quality forecasting in NWP with editors, myself and Jordan Powers. And the deadline for submissions has been extended. So if you would like to submit a paper, please do so. And with that, I'm going to finish, and I'm happy to take questions.
Thank you, Dom. I don't see any questions yet, so we do have time for one or two questions. So while people type, I'll ask you, since you have this special issue here about chemistry, can you tell us a little bit how CCPP is being used for chemistry?
All right. Yes. So the idea here is that the NASA has created a chemistry repository, GoCard repository, with a process library that contains all the core processes in a clean library, and that this component or this library can be used either through NUAPSI in the UFS or any other modeling system, or through the CCPP. And there's a lot of discussion going on to which extent this should be done, all of it in NUAPSI or all of it in CCPP, or key components like the aerosols that really belong close to convection or so, whether this should be done in the CCPP and the rest should be done in NUAPSI. Is that good enough?
Yeah.
Okay.
Okay, well, I don't see any other questions. So
I have a question. Sorry, I'm interrupting. Oh. Is it okay I ask a question?
Oh, yes, sure.
Yeah, hi, this is Peter Lauritsen from NCAR. Regarding your comment on computing derived variables such as potential temperature, yes. I was wondering if the CCPP would be able to support a functionality where parameterization would be able to query from some commonplace how to compute certain variables, such as enthalpy or energy, where different parameterizations may compute that in different ways, which leads to thermodynamic or energetic inconsistencies between them.
Yes, and we have discussed this, not necessarily within the context of entropy or so, but for example, when it comes to tridiagonal solvers, or when it comes to random number generators and stuff like that. So that idea is on the table, that we would have some sort of library, standardized library that gives people access to common ways to compute things, to transform things, and then hopefully we can make these, we can document them well, and we can make them as efficient as possible. It's not always easy, because, as you said, people have different preferences and use different ones, and everyone believes that his or her method is the method of choice. But I think we can agree. Once we can agree on something, we can implement that.
All right. Well, thank you, Dom. So I think we're going to bring this part of the program to a closing. Thank you to all the speakers so far. And I'm going to pass the word back to Bill Sachs, who will tell us what will happen after the break.
Yeah, thanks. Thanks again to all the speakers. Yeah, so we're going to take a break until about 3:30 and then return for an extended, for a presentation and extended discussion on CESM diagnostics. So we hope you can join us for that. And then I forgot to point out at the beginning, we are gonna, the session is gonna go until about 5 o'clock officially for this extended discussion time. And then we do welcome you to stay on after that. We'll keep this Zoom session open till 5:30 in case people just wanna stick around to informally catch up and chat and network afterwards. So we'll see you back here in about 12 minutes. Thanks.
Bill, do you want me to go ahead and share my screen? Or do you want to keep that up at the beginning?
Yeah, why don't you go ahead and share when you're ready? Thanks, Max.
You see it okay?
Yeah.
Max, are you still in Wisconsin? Or are you?
I am.
Back? Okay. Yep. Is it any cooler there? Or
it's like the low 70s. So.
Oh, that's nice.
Yeah, you might hear some boats cruising by in the background.
Yeah.
It's gorgeous.
Oh, nice. Yeah,
just dry.
It's crazy hot here. Oh, that's too bad though. Yeah.
Yeah, we've had a pretty bad drought the last few weeks, and looks like it could go on for at least another week and a half. So yeah, very dry.
Okay.
All right. Well, it's 3:30. So I guess we can get restarted here. And Max Grover is going to lead us off with an overview presentation of the current state of CESM diagnostics. And then he and some others organize a discussion around that topic. So yeah, take it away, Max. We're looking forward to this.
Yeah, so the idea of this presentation is kind of to get some ideas going and kind of spark some discussion. So this will be roughly 20 minutes long, and then we'll break out into small groups, have some discussion there, and then we'll come back together at the end. So I'll go ahead and get started then. So again, we'll sort of be talking about the current state of CESM diagnostics and some potential plans forward with these. So what do I mean by diagnostics here? So the kind of definition here is evaluation or evaluations of the results of a model simulation, which could be a comparison with previous observations, time series of some diagnostic to ensure that values are quote unquote realistic, and then it could be a model comparison. And why do we care about these diagnostics? So they're crucial to understanding how these models are performing, or they could possibly provide key scientific insight and could potentially lead to new knowledge. So a couple questions we're kind of after too is like, how have diagnostics typically been developed, and then what current packages or workflows exist? And so some of the traditionally used packages within CSM are the following. So sort of each component or each working group has their own diagnostics package. So for example, the AMWG diagnostics package, I'll go ahead and click here. So this is an example of the diagnostic output here. So you can go ahead and run all these and produce these static websites to be able to look at these diagnostics. So again, so for example, the CIS diagnostics package, the LMWG diagnostics package, the OMWG diagnostics package for the ocean output. And then there's also the variability diagnostics package, specifically the climate variability diagnostics package, or CVDP. So these are a lot of the traditionally used packages and sort of what's within the current CSM workflow. And so another one that I mentioned here at the end is the CVDP LE. So this is the climate variability diagnostics package that's made to work with large ensembles. And this is an automated analysis tool similar to the other ones, data repository for exploring these sort of the variability, climate change. So it computes modes of variability and trends in these different climate indices. The user specifies data sets, computes these ensemble means and spread, and provides this quantitative comparison to observations. It can read in monthly CMIP or CSM time series. It saves them out in .cdf files, and it's written in NCL currently, but calculations are being written into Python. And that the NCL story is kind of the overall story with our current diagnostics. The CSM post-processing is NCL based, which can sometimes be difficult to port to non-NCAR machines. It's serial in nature, and it can be tough to scale to finer resolutions. And basically, the furthest extent to scalability is being able to sort of process each variable separately. But if you're looking at a single variable, you wouldn't be able to kind of include or enhance the performance there. And then also NCL is in maintenance mode. And so the CISL's GeoCat team is working on transitioning NCL functions over to Python. And again, that's through the GeoCat efforts, which I'll talk about here in a little bit. So the problem is that a lot of this code base is written in NCL, and we like to move away from NCL, but obviously that's a lot of diagnostics packages. And again, so most of the community is also transitioning to Python, leading to several different efforts. So again, the GeoCat team is developing this Python toolbox for geosciences. So I mentioned in a talk yesterday, the ADF or the AMWG diagnostics framework is a new effort from the Atmos group. And then there's a couple other listed here, such as ClimPred, which is a lead time dependent diagnostics, and then this Model Diagnostics Task Force, which is a little bit more process oriented, but I'll get to that in a bit. And so kind of a summary of the current packages and proposed new development. So kind of breaking here down component, as you can see, a lot of these use the CSM post-processing package. And in terms of the new development, really the only component that's sort of committed to an effort so far is the ADF or the atmosphere group, but there's still uncertainty in terms of some of these other components. So hopefully that's something that will sort of make some progress here coming soon. And then the CVDP LE calculations are moving over to Python as well. So an update kind of on GeoCat, again, because I know a lot of people are heavy NCL users. So NCL computational functions are being migrated over to the scientific Python ecosystem through this GeoCat comp. So this is the computational library, and it builds on sort of some cornerstone Pangeo components such as X-Ray, Dask, and Jupyter Notebooks. It's relatively popular so far. And again, the motivation here is because NCL utilities are in maintenance mode. And the other kind of component of GeoCat is the GeoCat examples guide, similar to the NCL plotting gallery. So a lot of these use Matplotlib and CartoPy for visualization. They're presented in Jupyter Notebooks with detailed documentation, and they're partially supported by this Project Pythia, which is trying to provide training for people kind of making this pivot to Python. So example of this GeoCat examples page, so similar to the NCL gallery, they provide these sorts of examples and kind of provide a one-to-one from NCL to GeoCat. And the GeoCat team is very much focused on embracing open development. So community user contributions, and especially within the CSM community, providing feedback, helping identify and prioritize functionality needs. So especially some of the climatology related functions, it's good to know kind of what people are needing or using quite a bit. Responding to questions from other users. This was a big cornerstone of the NCL development, was just having a very strong support system. So that's something that's very important to the GeoCat team. And then reporting problems. So especially if you're using some of these tools within within GeoCat, make sure to report any issues you run into because that's really important. And then also being open to community developer contributions. So helping to develop new functionality or identifying existing functionality, and then also correcting problems and sort of taking that community-based approach where people can contribute. So an example of sort of GeoCat in action, specifically related to open development, is NCL's Venth2P, which I'm sure if you've ever worked with atmospheric data coming out of CSM, it comes out on those hybrid sigma coordinates, which a lot of the time you want to convert to pressure vertical coordinates. And so this was already on the GeoCat roadmap, but couldn't necessarily be prioritized. So on the left here is a screenshot of Zulip Chat, which is similar to Slack, basically a messaging platform. And people brought up the question about whether or not there's a function similar to this event2p, which was used quite a bit in NCL. And so after some discussion on there and sort of prototyping some solutions, some of the scientists in CGD were able to put together a pull request and contribute to the GeoCat code base. You can see the acknowledgement there, Brian Medeiros and Matthew Long and Deepak sort of acknowledged there. So this is an example where the GeoCat team kind of prioritized and implemented this with the help of scientists within CGD at NCAR. So collaborations like this obviously are going to be very important moving forward, especially related to diagnostic effort, and looking forward to continuing to collaborate with the GeoCat team. So the GeoCat provides a lot of the core functionality that will be used within the diagnostic framework. So as mentioned before, this is sort of the first first group that's sort of dedicated to sort of modernizing and moving forward with these new diagnostic efforts. So again, if you're interested, I know that there's talk yesterday about this during the atmosphere section, the atmospheric working group. So if you're interested in that, check that out. So the AMW diagnostics framework is this package that can be used to generate standard climatology comparisons as well as variability diagnostics, sort of all in one. It's Python based. It's a replacement for the AMWG diagnostics package. It's modular, where analysis scripts can be stored within these modules, and then you sort of have a main driver that's going through and putting everything together. So there's a link to the repository there, which is again very much under active development. And sort of the main aspects are averaging, regridding, plotting, and then looking at variability. And it's able to sort of look at and convert from history to time series, and it's able to integrate all the several other external packages, such as MBTF, CVDP, and any other relevant packages. So the idea is that the user would only have to import this framework, and it would go ahead and take care of a lot of that. Another example of a diagnostic package under development is ClimPred, which is a lead time dependent skill of initialized forecasts. So this is deterministic and probabilistic skill. It's able to, the current emphasis at NCAR is on subseasonal to seasonal forecasting, S2S, but should be adaptable to other time scales such as medium, range, and annual and decadal. And there's planned work on conditioning other large-scale states, such as NAO, PNA, and so on, for state-dependent predictability. And it uses Dask, which can read in data from disk or the cloud, and really helps with the performance using distributed computing. This is going to be really important for sort of working with those lead time-dependent diagnostics. And so some overall current collaborations. So we're trying to find common components of this workflow. So example of history to time series. So have an easy to use function for this. Another example would be regridding. So working with the GeoCat group and broader Python community in order to make regridding a little bit easier, and then also exploring interactive web pages in terms of visualizing some of these diagnostics. So the idea here, especially considering the amount of work going forward, is to find some of these key points of collaboration, work together to design this workflow, and then focus on developing these key components which can be shared. So we're using this Earth System Data Science initiative as the glue that can sort of bring us together, identify, prototype, and gather feedback on collaborative projects. So what exactly is Earth System Data Science? So it's a socio-technical network which strives to enable this collaboration. So it's more of kind of getting people together, solving these problems. Sorry, there's a boat going by. So the keys here are finding key points of collaboration adopting this agile approach in terms of prototyping some of these solutions and finding out what people are interested in. And then sort of the main components right now are using the Zula platform, this chat platform, using the Pangeo Discord, having these weekly meetings where we can kind of talk about some of these prototypes and, again, kind of iterate both with software engineers and scientists. We have a variety of blog posts kind of updating the community on what we're working on. So these are hosted on this website, and this link will be available after the presentation. So, for example, here's an example of building an intake ESM catalog for CSM2 history files. And then basically being able to produce these different packages, such as this ECG tools, which I'll mention briefly after this. So really, it's trying to find these key points of collaboration, again, moving forward on some of this. So a concrete example of ESDS in action. One of the kind of key aspects of any diagnostics workflow is being able to have an easy way to sort of read in your data. So we leverage some key components of the Pangeo community and the Pangeo packages. And so on the left here is example. So we have all these different components of model output. We're able to take this package, which basically takes all these files, puts together this data catalog where we can easily query our data set, look for certain components, streams, certain case, if we want to look for a certain frequency or even a certain variable. So for example, if we want to look for temperature from this data set, be able to query this basically database of files, and within a couple lines, be able to read this in and get a quick plot of our data. And this is from history file outputs. This even eliminates the need to generate time series files. So if you're interested in looking at this example and interested, this package has been released and sort of a write-up of this is provided at this link. But again, this could be a component that would be used within these diagnostic packages where you could basically parameterize being able to read in the data across its sort of component agnostic. So that's, again, very important in terms of developing this next series of diagnostic packages. And sort of another collaboration. So this is more sort of external as well as internal. So the Model Diagnostics Task Force, or MDTF diagnostics package, is a collaboration with NOAA, NCAR, UCLA, GFDL, CSU, LLNL, and then DOE. So pretty wide, and then there's several other universities and institutions that are involved with this. So this is a diagnostics package that's more so focused on process-oriented diagnostics, as you can kind of listed across here across the figure. So MJO teleconnections, diurnal cycle of precipitation, MJO spectra. So sort of more focused on some of those process-oriented as opposed to mean or variability diagnostics. And this effort, so this diagnostic package currently allows for multiple environments and languages such as both Python and NCL. So as you can tell, there's quite a few efforts going on, and the diagnostic community overall is moving more towards these scalable workflows within the Python ecosystem. And several groups have already started this effort. So GeoCat kind of putting together some of the basic tools that will be used, ADF providing kind of leading the way in terms of putting together this framework, and then CVD-PLE in terms of some of the variability diagnostics, and especially working with some of these large ensembles. So overall, we need to continue to find key components of collaboration within our workflows, such that we can reduce the amount of duplication of effort as we push forward. So again, there's relatively limited resources towards some of this. So hopefully some of that collaboration will lead to hopefully improving and making this a little bit more efficient. And then we want to continue to train other software engineers and scientists to contribute to these efforts and find external collaborators too. So kind of even looking outside the NCAR organization, especially the CSM community, people to help with some of this, again, because it's a large undertaking and something we're looking forward to collaborating on. So at this point, so after this, I'll kind of take a couple questions, but I just wanted to sort of introduce. After this, we'll go ahead and go into some small group discussion. kind of answering some of these key questions. So how do you incorporate diagnostics within your workflow, and what diagnostic package or packages do you currently use? What features do you think are required before you would use a new diagnostics tool? And given how much of the diagnostic development comes from volunteers in the user community, how could you and your colleagues contribute? And then also, how could we better enable your contributions to some of these diagnostic efforts? So at this point, I will take any questions you might have before we break out into discussion. But I'm really looking forward to some of the discussions and moving forward on some of this.
Thanks a lot, Max, for that introduction. There's quite a lot of questions in the chat already. I can go ahead and read some of those to start off. Well, let's see, there's first a clarification from Dave Bailey. He says, the CESM post-processing uses Python packages PyReshaper and PyAverager to create climatologies and time series. These are parallel. And then the MCL code is used mainly for plotting. That's also task parallel. That is, multiple plots can be drawn at the same time. So I don't know if there's any.
Yeah, and I do know that. So for example, the PyReshaper and PyAverager, a lot of that is, so yeah, it's parallel, like it's run in parallel. But again, at the core of it too, you can only do one variable at a time. So especially if you're working with some of these large ensembles, for example, a little bit more challenging, but yeah.
All right, oh, let's see, scrolling faster than I can get it. Okay, here we go. From Alice DeVivier. She said, maybe I misunderstood this, but I thought we were moving away from having history files available and wanting everything to use time series because those are smaller to store. Is that right, or is that a misunderstanding?
Yeah, so I'm not I'm not really sure what the stance is on that. The idea with sort of using history files in that example was to sort of show that that you wouldn't necessarily need to do that conversion, but it's flexible enough where it could work with time series as well. So whether you're working with time series or history, at least that tool, it doesn't really matter as much. But.
Okay. Lisa asks, are all the diagnostics that you've discussed, are they all being run offline? That is, they run after the modeling system has written output to disk, or are some of them in line with the model runs?
Yeah, so typically the post-processing is run after your model run is done. I don't know if David, do you want to answer that all?
Well, I already typed it in. Actually, the CSM post-processing is built into the run workflow, so you can actually launch it at any point in time during a run. And that's often what's done is if we're running like a 100-year production run, sometimes it'll automatically kick off the post-processing 50 years into the run, just so that we can assess and decide whether to keep running or not.
Okay. Thanks. I think the rest of the questions, if I'm following right, have either been answered or are just answers in the chat. If people still have a question, please feel free to repost or raise your hand. But Kate, I see, looks like you have a question.
I was going to make some clarifications, but I'm not sure I've kept up with everything here because that was a little while ago. I think that the person asking about running or doing the diagnostics during runtime, it does depend on how you consider during the run. Dave Bailey is saying, like 50 or 100 years into a run, you've stopped the model at that point and you're looking at the history that's been produced up to that point. You can't really run these on history that's currently being produced by a model that's actually running it while it's going. I can't remember what else I was going to say, so I'll just put my hand down.
Yeah, and I just want to make a correction. So yeah, PyReshaper, which is being used, can convert history to time series in parallel using MPI, and all variables are done at once. So that was kind of the way it was designed. So yeah.
Let's see, there's some questions and comments going on about how much and whether there's actually space saving going from history to time series. And I think my understanding from the chat is is that actually there's maybe a slight increase in going from history to time series if you're using the whole, if you still want the whole data set. But the advantage of the time series is that you can transfer individual variables, just the ones that you're interested in. Others can chime in if that's correct or incorrect.
There is a subtle difference here too, that each of the history files contain the grid information and the metadata in every single one of those files. And so when you run the time series on it, then you end up with just one copy of those variables in each time series file. And that's actually a significant savings.
And if I can interject, there's another issue, which is that data that's written straight from the file in history form, data that's written straight from the model in history file format, those things are not compressed. The PyReshaper can compress them. And so usually what happens is in the conversion from history file to time series, what you end up getting is lossless compressed netcdf out, which is smaller usually than what you started with. But the real problem in terms of data usage is the fact that you keep both of them, history and time series, therefore, a little less than doubling your data usage to keep both formats.
Yeah, I think I've heard that best practices now, and I think Günther may be about to say something about this, is that you convert your files to time series, you decide which variables you want to keep, and then you get rid of the history files that are left behind. Or you compress all your history files and don't convert them to time series, one of the two.
Let's see. Brian, do you want to take your chat discussion to
Sure. Yeah. So I don't know much about post-processing of data, but I'm on a project where there's some discussion about whether we're going to time series or keeping history. And I've been having this in the comments discussion with Kevin. And the answer for why you might want to go back is that if we have communities that can't open, so there's some question, can MATLAB read ZAR files, which are time series? Can we go back from a ZAR and recreate a netcdf history file from that?
Okay, so I think it really depends upon what kind of things you want to do with the data set. There is no perfect format for every analysis out there. If you want to go ZAR, there's no reason that it has to be time series. It could be something in between time series and, so what you're talking about with ZAR is the chunking of the files, the chunk files. And there's no reason why you'd have to chunk it in a time series like format. I think it's a very, very difficult question to answer. I mean, the real question is, why do you want to keep changing the format? What's motivating that?
Yeah, so I think that in this case, it's not, it might be a case where 80% of a community is served with one format, but 20% might need another. And so I just simply didn't know if you could go back and convert between the two. If you can, it's not a problem. You do what's dominant. If you can't, maybe that's a problem.
Right. So the PyReshaper is a one-way operation, but once you've converted it to ZAR, you can rechunk at will, which is one of the advantages to ZAR. So if you want to change your chunking scheme from what essentially looks like a time series operation to something that looks like a history operation, you can do that. There's nothing that prevents you from switching them at any moment. But yeah, I mean, if you're trying, if 80% of the community needs or is best served by one particular format, and 20%, as in your example, is served by a completely different format, then I might recommend the 20% producing those on the fly for a particular analysis and then deleting it.
Dave, go ahead. You had a question or comment?
Yeah, there's another monkey wrench in this, and Gary Strand's not here, so I'll bring it up. And that is the extra step of then making things CMIP compliant, you know, which is another ugly step in the process. And you know, so it's standardizing the time axis, and it's converting variable names to standard CMIP names, and you know, things like that. And so, you know, it's just, that's something else in this time series post-processing that often sort of gets left out. And you know, and it's, you know, some scientists are more used to using the CMIP compliant formats, you know, and so it's, you know, ideally what would be happening would be that the models would be writing CMIP compliant right from the get-go. And I think, as Jim's sort of alluding to as well, having that ability to write directly from the model into a time series format. I think those are sort of some of the best strategies, I think, and we've been talking about for years, but I just wanted to contribute that back to the discussion.
All right. Given that it's the top of the hour, there are still, I think, a couple more questions or comments in the chat. But Max, do you want to move on to the discussion, and do you want to kind of introduce that?
Yeah, I'd like to move on to discussion. If people want to bring those up after and sort of when we come back to this larger group discussion, that'd be good. But yeah, so I'd like to sort of break off from these small groups. Yeah, I'd like to start up the breakout rooms. So
Elizabeth, are you going to get those started?
Yeah, so we'll need 8 breakout rooms.
Elizabeth,
are we just going to be randomly assigned to a breakout room? And
Yep. Yeah, so you'll be randomly assigned to those breakout rooms, and then I'll just ask that the moderators that I have assigned, that you go to the number of of breakout room that you were assigned, so I can go ahead and drop the document there again. But
cool.
Yeah, I don't know if Bill, do you have the ability to?
I do. I'm not hearing back from Elizabeth, so let me see. I haven't done this before. Now I'll try to figure it out.
I'm sorry, I'm here.
Oh, you're there? Okay.
Yes.
Okay. So we're ready for the eight, right, Max? The 8 breakout rooms?
8 breakout rooms, yeah.
Great. Okay, I'm gonna go ahead and stop recording though.
Okay.